Okay, SL kids, we're going to do discussion 8.2, weak acids and bases and salt hydrolysis. This is the final topic in Unit 8, and some kids find it a little challenging, so please study hard. Okay, we're going to start with some calculation practice with neutralization and dilution of strong acids and bases. Right, so determine the pH of the solution resulting when 100 cubic centimeters of 0.5 molar HCl is mixed with 200 cubic centimeters of 0.1 molar sodium hydroxide. Alright, so we have to first figure out what happened. There's no specific formula to use with these problems. Right, we just have to determine what happened. So we're mixing an acid and a base, so we're going to get a neutralization. Right, now, we have to first determine which acids and bases are being mixed. Now, if the number of moles of H in the acid is equal to the number of moles of OH in the base, then that means it's a 1-to-1 mole ratio. You can write the equation for the neutralization of hydrochloric acid with sodium hydroxide, and you see the mole ratio is 1-to-1. All right, so we have to determine whether there's a complete neutralization or if there's excess acid or excess base. So the easiest way to do this is to find the moles of each. So we know that we can find the number of moles of solute if we multiply the concentration of the acid times its volume. So to find the number of moles of hydrogen ions, I will take the volume in cubic decimeters, 0.1, multiply it by the molarity, and I get that there's 0.05 moles of H+. When I do the same thing for the base, I see that we have 0.02 moles of hydroxide. Now, with 0.02 moles of hydroxide, you would only be able to neutral 0.02 moles of hydrogen ions because it's a 1-to-1 mole ratio. Right? So we're going to figure out how much excess we have. To do that, all we have to do is subtract the number of moles of hydrogen ions, or subtract the number of moles of hydroxide ions from the number of moles of hydrogen ions. Right? So when I do that, I see that we have 0.03 moles of hydrogen ions remaining. Now, if I want to find out the concentration of hydrogen ions, I just have to determine the new volume. Well, we had 100 milliliters of acid mixed with 200 milliliters of base, which gives us a new volume of 300 milliliters. When we convert that to cubic decimeters, we get 0.3. So the concentration of hydrogen ions will be 0.03 divided by 0.3, or 0.1 moles per liter. Now, you may think you're done because you've calculated something, but you have to remember that you're asked for the pH as well. So pH is negative log of the hydrogen ion concentration, which in this case would be 1. Okay, next, 200 cubic centimeters of a 0.1 molar HCl solution are mixed with 100 milliliters of a 0.5 molar HCl solution. So what is the concentration of hydrogen ions and the pH of the resulting solution? So again, we really need to figure out what is going on here. This is not a neutralization. We're just taking two hydrochloric acid solutions and mixing them together. So I'm going to give you a little analogy. Let's assume that you have 2 glasses of water. Each glass of water has half a liter of water. Okay, so the total volume of the 2 glasses would be 1 liter. Now, if you had 2 ice cubes in one and 3 ice cubes in the other, if you mix the 2 solutions together, you would have 5 ice cubes over 1 liter. Right? So we would calculate the concentration of hydrogen ions the same exact way. If we figure out the number of moles in each acid and then divide by the total volume, we'll get the new concentration. So in the 200 milliliters of 0.1 molar, there'll be 0.02 moles of acid. And in the other solution, we have 100 milliliters of 0.5 molar, so we'll have 0.05 moles of acid. When we add them together, we get the total moles of hydrogen ion will be 0.070 moles. Right, now we just have to figure out the new volume. Again, 200 plus 100 is 300 cubic centimeters, which is 0.3 cubic decimeters. So we'll calculate the new concentration by dividing the moles by the volume, and we get 0.23 moles per liter. That should say to the negative third. And the pH is the negative log of that concentration, which is 0.64. So again, when you do these problems, don't just do it and think you're done. Actually consider what you're being asked for, because you know how to do this. Alright, so what is a strong acid or base? A strong acid will dissociate completely in water. That means if you have 1 mole of hydrochloric acid or hydrogen chloride gas and dissolve it in water, you'll have 1 mole of hydrogen ions and 1 mole of chloride ions. The whole compound will completely break up into ions. So we don't use a double-sided arrow for showing this, right, because it's not a reversible process. If you put HCl in water, it will all break apart into its ions. The ions will not go back together and form HCl. Right? So a weak acid, then, is an acid that does not dissociate completely. So the general form of a weak acid would look like this, where we have general acid HA in an equilibrium with hydrogen ions and the conjugate base. All right? So we use a double-sided arrow for a weak acid because it's not completely dissociated. And it actually does form an equilibrium system. So if we're going to do ethanoic acid, there's the formula for ethanoic acid. We would show it with a double arrow, dissociating into hydrogen ions and the ethanoate ion. Okay, so these are some common strong acids and bases to know. You have to know these. So the acids are hydrochloric acid, or HCl. We're well familiar with that one. Nitric acid, or HNO3, and sulfuric acid, which is H2SO4. Now, there are other strong acids in the world, but since the IB only requires you to know these 3, if it's not one of those 3, you can assume that it is a weak acid. And strong bases are all group 1 hydroxide compounds, so sodium hydroxide, potassium hydroxide, lithium hydroxide, etc., as well as barium hydroxide and calcium hydroxide. Now, you're more likely to see the group 1 hydroxides used as examples because barium and calcium hydroxide, although they are strong bases, are not very soluble, and that kind of creates some problems. All right, so just want to note, when a base is dissolved in water, it is called an alkali, or an alkaline solution. If you remember from Unit 2, sodium and magnesium, those oxide compounds of those elements, form bases in water, right? That's why they're called alkali and alkaline earth metals. All right, so some weak acids and bases you may have heard of. Again, this is just for your information. You don't have to memorize these, but citric acid is what we see in citrus fruits. Ascorbic acid is known as vitamin C. Acetic acid, which we call ethanoic acid, is what makes vinegar what it is. And for a weak base, we have ammonia, which is NH3, and that's found in a lot of cleaning products. All right, so one thing you have to do is determine whether equimolar acid solutions are strong or weak. When we say equimolar, we mean they have the same concentration. All right, so one of the things you can do is react it with metal. Now, if you have equimolar solutions of a strong and weak acid, you'll see a much more vigorous reaction with the strong acid because it is fully dissociated and the weak acid is not. Next, you could test the conductivity because the strong acid has more ions in solution. It will be more conductive than the weak acid. Or you can measure the pH. Now again, it's only useful to do this if they're the same concentration, right? You're going to have highly concentrated lemon juice that shows a lower pH than very, very, very dilute hydrochloric acid, right? So this only works if the solutions are the same concentration. Since the strong acid is more fully dissociated, it's going to show a lower pH. Right. Distinguishing between acid and base. All right. So this is pretty obvious. You could just do a pH measurement, right? The base will obviously show a higher pH than an acid. You could also do a reaction with metal because if you recall from topic 1, bases do not react with metals and acids do, at least with some metals. Okay. Finally, you could mix both solutions with an acid and a base, right? We know that a neutralization is an exothermic process, so if you mix an acid with an acid, you get maybe a slight temperature change, but not nearly as much as if you mixed an acid or a base. All right, so KW. What the heck is KW? You recall from Unit 6 or 7, either or I guess, that capital K is an equilibrium constant. And so K sub W is the equilibrium constant for the auto-ionization of water. And what the heck is auto-ionization? Well, a small amount of water will naturally dissociate. So we see here liquid water will break up into its ions hydrogen and hydroxide. And now this doesn't happen in very large amounts. But if we wrote the K expression for this equilibrium, we would exclude liquid water because we exclude liquids. So it's a very simple K expression. KW is equal to hydrogen ion concentration times hydroxide ion concentration. So in pure water, both the hydrogen and the hydroxide ion concentration are 1 times 10 to the negative 7. So the equilibrium constant for the dissociation of water will be hydrogen ion concentration times hydroxide ion concentration, which will be 1 times 10 to the negative 14. All right, and this is actually how the pH scale is derived. So let's have a look at this. So there's our K expression for the dissociation of water. And now if I can take the negative logs of both sides of this equation, just because I can, and you get negative log of hydrogen ion plus negative log of hydroxide ion equals negative log of 1 times 10 to the negative 14. Well, we know that the negative log of hydrogen ion concentration is pH, and the negative log of the hydroxide ion concentration is POH. So, and the negative log of 1 times 10 to the negative 14 is 14. So this is where we get our relationship that pH plus POH equals 14. It's not something that's actually just made up, which is cool. All right, salts. All right, so what the heck is a salt? A salt, as we know, is the neutralization product of an acid and a base. Right? And a salt is formed when the anion from the acid joins up with the cation from the base. And for a couple of examples that we've seen, hydrochloric acid with sodium hydroxide, cation from base joins up with anion from acid to make sodium chloride, potassium hydroxide and sulfuric acids, potassium sulfate, and so on. So the general rule, the weaker an acid is, the stronger its conjugate base will be. And the weaker a base, the stronger its conjugate acid will be. Right? So this comes into play when we talk about hydrolysis. So because the conjugate base of a weak acid is a strong base, it will hydrolyze or break apart water, as we can see with HF. So the conjugate HF is a weak acid. Now we know it's a weak acid because it's not one of the 3 strong acids that we have to know. Okay, so because fluoride is the conjugate base of a weak acid, it is going to serve as a strong Bronsted-Lowry base. So it will pull a hydrogen atom or a proton off from water to produce HF and a hydroxide ion. Okay? So we say that this is a strong base because it produces hydroxide ions in water. Another example would be aluminum hydroxide. So we're only concerned about the conjugate base, which in this case would be the aluminum 3 ion. So aluminum 3, because it is the conjugate, of a weak base, it serves as a strong acid. Right? So it will produce hydrogen ions in water and take the hydroxide ions from water to make aluminum hydroxide, or aluminum hydroxide. I almost said 3. Okay, so this shows us how this is just an example of how the conjugates of weak acids and bases are strong. All right. Now, the conjugate of a strong acid or base will not hydrolyze water, and to see an example of that, we'll look at chloride, which is the conjugate of hydrochloric acid, a strong acid reacting with water. Right? If chloride ions were to hydrolyze water, right, they would be serving as a base because it's the conjugate base of an acid. So if they were to do that, they would make HCl and OH-. But we know that in solution, HCl will completely dissociate into chloride and water, right? So we'll just be back to where we started from, and the water doesn't break apart and there's no change. All right, so let's look at some examples. So we have to know whether a salt is acidic, basic, or neutral, right? So we have to consider the nature of the cation and the anion, right? So for sodium carbonate, sodium is the cation from sodium hydroxide, a strong base. And the carbonate ion is the conjugate from carbonic acid, a weak acid. Right? Because that anion comes from a weak acid, it will serve as a strong base, and so the solution will be basic. All right? Now, that's the reason why, but the explanation is just the cation is from a strong base and the anion is from a weak acid, so the solution will be basic. Now, for aluminum chloride, we have the cation from a weak base, and the anion from a strong acid. So the solution will be acidic. Okay, so summing up, if the salt is the result of a strong acid and a strong base, then the pH will be near neutral. If it's a weak acid and a strong base, then the pH will be basic. and so greater than 7. So strong base and weak acid, ethanoic acid, produces sodium ethanoate and water. Right? Sodium ethanoate would be a basic solution. If it's a strong acid and a weak base, then the pH will be lower than 7. Right? So we have ammonium hydroxide and hydrochloric acid. We have the cation from a weak base and the anion from a strong acid. So this will serve as a strong acid. Okay. Now, if you have a weak acid and a weak base, it depends. Right? It depends on whether the acid or base is stronger. So I don't anticipate you'll ever see that situation. All right, so I want you to practice this. Pause the video and try to determine, based on the identities of the cations and the anions, if these solutions are acidic, basic, or neutral. All right, so sodium chloride. Sodium is the cation from a strong base, and chloride is the anion from a strong acid, so the solution will be neutral. Next we have potassium ethanoate. Potassium is the cation of a strong base, and the ethanoate ion is the anion from a weak acid, so it will be a basic solution. Aluminum chloride. Aluminum comes from a weak base, and chloride comes from a strong acid, so it will be acidic. And sodium fluoride, we have strong base with weak acid, so it will be slightly basic. All right, now this is why this is important. This is a question that was on last year's SL paper 2. It says, outline what is observed excuse me, when magnesium powder is added to a solution of ammonium chloride. So whenever you're asked if a metal is put in a salt solution, what the nature of that salt solution is. Now we know ammonium chloride comes from the cation from a weak base, ammonia, and the anion from a strong acid. Right? So because that's the case, the solution will be slightly acidic. Now we learned in topic 1 that when metals are put in acidic solutions, you will see bubbles produced, and those bubbles will be hydrogen gas. All right? So this is the answer that they were looking for in this question. Either these words or this equation. Solid magnesium plus aqueous ammonium chloride making hydrogen gas, ammonia, and magnesium chloride. Right? So this is definitely something that you could be asked, and so I would definitely expect to see it on your test. All right, so if anybody has any questions, please bring them to class, and thanks for watching.